is David Glenn. This is the Virtual Planet Builder Quick Tutorial 2. Before we get started with part 2, I'm going to start with a quick recap on what we covered so far. In the first video, we went through a step-by-step process and how to compile all the elements to make Virtual Planet Builder. Yes, for the most part, part 1 may have been a little too detailed for some. I felt this was necessary to explain the process, not only how to build Virtual Planet Builder, but also how to build OpenSceneGraph in general, which I don't see too much instruction in. By the way, if you missed any part of part 1, I have the link right here, so you can recap the video. But to cover it, kind of gloss over a reintroduction to it, this recap included pre-installing functional libraries for OpenSceneGraph and Virtual Planet Builder, installing the Python for supporting functions in GDAL. Since we're covering MS Windows, we use Python 2.7.1. We also installed GDAL itself, version 1.11.0 for Windows, as we want most of the functions in OpenSceneGraph and Virtual Planet Builder to use geolocation and processing georeference data. We needed the OpenSceneGraph. Finally, we installed the libraries and the include files for GDAL that will run under 1.11.0 and a location that we can find them. We proceeded to prepare and compile OpenSceneGraph and Virtual Planet Builder for use in Windows. We gathered the source of OpenSceneGraph and gave it a location. This included preparing OpenSceneGraph for compile in Visual Studio Express 2010. We used CMake to locate all the proper library files that not only included the GDAL stuff, but that we use for the georeference. But also we took advantage of some of the libraries that other libraries that comes with the development distribution of GDAL that we can take advantage of for other image formats that we might need. We completed the compile of the OpenSceneGraph libraries using Visual Studio Express 2010. We then proceeded to prepare Virtual Planet Builder using CMake to find all the necessary library files, which was a lot simpler than that we needed for the OpenSceneGraph. And then we proceeded to compile that using the Visual Studio Express 2010. We went through post-processing of the OpenSceneGraph and the Virtual Planet Builder DDLs, plugins, and binaries for to make it easy for command line use in Windows. This included gathering the necessary files that are used and placing them into a common directory, which we could find. It would be easy to find in the system. To make it easy to find, we modified the path environment variable to include our new common directory, so we could run commands anywhere we want and build our maps. We went through a testing process to make sure that both OpenSceneGraph and Virtual Planet Builder were functionally viable, and that it didn't have any DLL exclusion errors. There was some things to note in the first tutorial about compiling Virtual Planet Builder and using Visual Studio. There is an issue in the VPB.DLL where Visual Studio thinks there is multiple decorations in the code, which arguably there is not, but they say according to the authors it's a bug in the linker, which is probably debatable. In order to compile the code, however, to get by this, you will need to go to into the linker and disable multiple decorations, which is not that hard to do. So VPB.DLL will compile. Without this, of course, the main program that we're going to be using today, which is OSG DEM, will not function because this DLL has all the functions that that program needs to run. Disabling these disabling multiple effects should not have an effect on the operation of Virtual Planet Builder. So we should be okay in that respect. In this tutorial, we will take what we have compiled and we'll gather data and show how Virtual Planet Builder works. So without further delay, let's go on with part 2. So let's do some historical recap. What is Virtual Planet Builder anyway? Basically, Virtual Planet Builder was a tool originally written by Robert Oldfield. It was started by him and a few others that contributed over this effort to make this map building tool. It is used to make terrain ideally for OpenSceneGraph and OpenSceneGraph based projects. Virtual Planet Builder maps that I happen to make use geocentric, or what's called, or Earth-centered, Earth-fixed, or ECEF maps. For me, ECEF is more practical to use with some of the built-in OpenSceneGraph functions like the coordinate system node for the placement of objects using common geographic coordinates. So one thing to know about Virtual Plant Builder, which is its very distinct advantage, is it builds what's referred to as a page database. This allows OpenSceneGraph to display large areas of terrain without a huge impact on memory on the system. The concept about paging boils down to it will when the program starts, it will load the database depending on what of the terrain is visual in the thrustum. When you move closer or farther away, the level of detail kicks in, and rather than just go sorting through the level of detail in memory, it will get to a certain point and it will throw out certain map data when it's not practical to use and bring in other chunks of data in a very quick manner. You may ask yourself, how big can you build? How big of a database can you build, or a terrain can you build with Virtual Plant Builder? Well, the reason why they call it Virtual Plant Builder is it could practically take on the world if you have enough data. Since the terrain is made up of many files, your limit is usually the size of your hard drive, because big, highly detailed files can take up huge chunks of data for big areas. The average database that I have made can cover an area like California, Nevada, and Arizona, combined using satellite data at 15 square meters of land space per pixel, or what is referred to as 15 meters of resolution. The resulting files can take up to 30 gigs of hard drive space or more, depending on the detail. So, what will we cover in part 2? Well, subject involves terrain that is like any other model system, can be vast and dynamic. And so I'm going to focus on, for this tutorial, since it's introductory, I'm going to stick on one little part of Virtual Planet Builder, and that is OSG-DEM. OSG-DEM is basically the workhorse of Virtual Planet Builder. The rest of the system is merely to manage how many versions of OSGEM is running at any given time, since you can do what is referred to as render farming with Virtual Planet Builder. Also in this video, of course, we will cover how to get the data. It's not much. Virtual Planet Builder isn't very good for you unless you know how to get the data, and I will go over that in this tutorial. I will also go over what you may have to do to process the data. The data in this raw form probably is not fit. Usually it's not fit for Virtual Planet Builder immediate use. So you sometimes have to go through and process it. After you process the data, you'll need to build up a command string, since it's OSGDM is a command line based function. You do need to have some knowledge of the basic command line functions. I will go over something that is simple and I know works for me. There's probably other functions out. There's a lot more functions to OSGDM than I could possibly go over in this tutorial. So I'll try to go over the simplest of the bunch. Finally, after we build our database, we need to be able to test it and make sure it is fit, and I'll be doing that using OSG Viewer, and I will show off some of the components of the program in a form, and basically just go over how to test the results. So let's get started. But first, let's go over GDAL. What is GDAL? GDAL is the tool that is used by many digital map makers to process images that happen to be georeferenced. GDAL could also be used to process elevation data that is known as Digital Elevation Model, or DEM data, for processing in the topography in terrain. One of the examples, other than what's used in what we're using here in this tutorial, is to make map backgrounds using DEM data. This is something that I will probably cover on a paper on a later date. GDAL is used in Virtual Planet Builder, as I suggested earlier, for transforming raster data into polygons that represent the terrain, the topography of the terrain. And it's very ideal to learn as much about GDAL as you can over the course of time. To do so will empower you and allows you to make better maps using various forms of map data. Good map data, of course, will translate into good terrain. Like anything else, it's garbage in, garbage out. Good data in, great maps out. In this slide, I bring a good example of what is something that that is can be built utilizing certain functions in GDAL, like the topography which is used in this Hemet Terrain. This was based on digitized USGS topographical maps, which was cut using a tool that's based on GDAL. It was used. It was the elevation maps that are in here were created using a function of GDAL, which processed the DEM data, and the terrain themselves have to be processed first by editing out the borders when it comes to a classic typographical map, and GDAL is one of the few tools that allow you to deal with, cut through this without having to worry about losing your georeference data, because it will go through and cut out and reorganize any georeference points to fit that data, and it will do it painlessly. Also to note, GDAL is made up of also a set of libraries. That's obvious because both OpenSceneGraph and Virtual Planet Builder use them. They're good library. There's some good functions in those libraries that are ideal for any programmer that wants to handle this data. Could use. GDAL is primarily used as a command line tool and to prepare visual data. But since GDAL is a graphics manipulation tool and it is command line, is there, it begs the question, is there any GDAL GUI out there per se, kind of like a front end that you can use to handle map data in GDAL and do it in even a more painless way, more graphical way? And the answer is yes. QGIS is got its original start, I think, as a front end for GDAL. It also handles many other functions, but the idea between QGIS, which is written basically by the same group that wrote GDAL, is to have a nice graphical user interface, like a graphics editor that incorporates GDAL functionality into it. QGIS works under Windows, Linux, Mac, and there are even plans to do an Android version of it. Oddly enough, though, not a version for iOS. Oh well. QGIS has many more tools and plugins, as I've kind of hinted on before. Too many to talk in this video, but there are some good ones there that are very useful to know. So here's an example of QGIS in use, displaying the Hemet Terrain Example that I'm going to show you today. What you're looking at in the GUI is both the dim data, which is the black and white background that kind of rings around this map. What you're seeing in the center, of course, is the topography map that came from the USGS. This has been trimmed so you can use it in a map form. Otherwise, it comes with these borders, and those borders are not very useful for our map, so we have to cut them away somehow. So we used QGIS, and we'll get into that in a little bit. So now that we've been well introduced to GDAL and QGIS, and we know what tools we're going to use to edit our data, let's go get some data. So the question that usually comes up about this time is, okay, I got these cool tools. What are we going to use with this stuff? And there's probably several good sources to get georeference data. Some of them cost money, but I'm going to try to concentrate on North America and data that is available to the general public. And for that, I tend to fall upon the U.S. Geological Service. They've been making maps for ages, so they really know their business, and they have some pretty good map data. Some of it is available through some portals that you can download data from. The most popular being Earth Explorer, and not quite as popular, but just as useful, is another one called GeoViz. And then there's one that handles PDF format maps, which is something I've not used terribly much in map development, but is there anyway, and it's referred to as the PDF format map downloader. For our friends in the north, Canada has a service that is referred to as GeoGravis, to get where you can get data for Canada. Canada data tends to be a little more easy to process. I haven't really gotten too much detail out of the free data you can get from Canada, but it is there. I used it when I did one of the maps when I was given this talk at SceneGraph in Vancouver. And even though both sites are free to download the data, in some usually the cases in some of the data is you will have to register and establish an account. It is free, but it does take a little time to deal with that. I'm sure there, as I said before, I'm sure there is a lot of better sites out there to get data, but for first timers and for those who are just breaking into it, USGS is a good start. So we're going to look into using that. For this video, I'm going to use the USGS Earth Explorer, which has a easy to use GUI. Using this is quite simple and forward. You select an area which you want to grab data from, as is demonstrated in the slide. Hello, we're over here at the USGS Earth Explorer. I already have logged in, so we're ready to grab our data. And for starters, we're going to zoom in, and I'm just going to do a use map capture of this data that we're going to need, and that should be sufficient for our purposes. And for starters, I'll zoom in. I'll use my zoom button, my mouse wheel, to zoom into about approximately where I want to go, and zoom in again and center in on Hemet, because that's what we're going to do. And I'm going to put that back up, and center in again until we get to the area that I want. And I think that will do for now. So I got the area. I hit use map and I get 4 instant points. Now I can back off on this and you can see that we have points. They're all numbered 1, 2, 3, and 4. They correspond with the data entry points that I have here. 1, 2, 3, and 4. We can adjust these with you as you like just by moving the little pins here, but I'll avoid doing that right now because I don't want to screw this up too much. This is exactly where I want everything to be. So I'm going to go ahead and hit data sets, and then I'll get this nice little menu of data of data I can get. But the first thing I'm going to do is I'm going to get some dim data, and to get that I'm going to go over and get this Aster Global Dim. This is exactly what I want. And when I click this, a warning screen will pop up saying you have a data. You have selected a data set that has data restrictions, and you're supposed to read this, and I guess everything's done by the honor system is how it's used, but we're using it for non-profit hobby purposes, so I don't see it's going to be a problem. Hit OK, and after all, how else am I going to demonstrate this to you? The next thing I'm going to need is some digital maps, and I'm going to use DRG maps, which is basically the USGS topographical maps, the same maps that they use for, well, they used to produce these used to be hand-drawn and, very articulately done and accurately done, and used by hikers for trails and water holes and camping spots and such. And that's what we'll use those here. So I'll select that. Now, there is a thing here called additional criteria. And for the dim data, we're not going to worry about that. Also for the DRG data, even though we can get quite extensive, I'm not going to worry about it. I'm pretty satisfied that I can pick out what I need using the selection that I have. So I hit results, and right off the bat we are looking at our DRG data, and we go over and we hit over here to the data set, over here it's called DRG. Go over here and go to Ulster Global Dim, and there's our dim maps, and we got pictures here to show what it is. And we got this little thing on the side here which says footprint, so we can do a footprint, and voila, there's our maps. And there's another. And I could go over the process of downloading them, but it sometimes takes quite a long time for it to do, because these are huge data maps. And so instead of doing that and dragging this video out, needlessly long, I'm just going to say click on this. You'll get a little thing that says you agree to the terms. Say I agree, hit download, and the download should start. When it finishes, you should be able to go back to this map here and get the other map data, and then you can go ahead and move on towards your DRG data. Now the DRG data works pretty much the same. You got a footprint. In this case, we don't have little footprint images of the thing, but we can see where they land. like right off the bat. We can see part of it lands about here, which is about what, so we need that chunk of data, so we'll note that. And same here, and we'll go on and say there's more of it, and more of it, and so oops, it's a little on the big side. That I don't need, so I'll deselect that. I won't pick that one. And then, oops, there's the other one. Also don't need that, so I'm going to go and deselect that. I won't pick that one. And so these two files here, we're not going to touch. And there's a way to exclude this through the database from future searches, and that is by selecting these right here. And these basically say these are banned from future searches, but I won't select those today. I'll keep going on. Go over here to the next one. Yeah, I want that, and I want that, and I want that. And let's see, continue on down. I want that. And you will go down after you download this stuff. It's basically the same process. You'll go over here to page 2, and everything will go blank. But you go over here and say, "Ooh, I don't want that one." And here again, you can probably ban that from scanning because you'll probably want the most detailed map data you could possibly get, and that is not too detailed, I'm sure. And then we got that and that pretty much covers the base. Download those two elements and we'll pretty much have our data. And that's basically how you get your data. It's as easy as that. And in fact, I'll go over here and I'll start a download. Yes, I want to download that. And automatically, it'll start to download right here. So that's basically it. You can go through and check out the various forms of map data and collect what you need. And I got this file, so I can go ahead and go click, and that's gone. And then I can go to the next one and go collect that file and download, and it will go ahead and download that one. And we'll just proceed on this. I probably don't need to run the video how to do this because you pretty much, I'm sure if you know how to run a browser, generally you know how to download these files from this point forward. So that's basically it. Thank you. After you've gone through the process of downloading your data, and these topographical maps, as I mentioned before, they're digital representations of what used to be the printed maps that you would get from either from camping supplies or the Ranger Service, from the U.S. Forestry. That's where primarily a lot of this stuff was used, and by hikers and such. And what we want to do though is we want to take a chunk out of this so we can mosaic this stuff across our map without the borders. And to do that, that's where QGIS comes into play. And the next thing I'm going to do is tell you how to prepare the data for this. So as you remember before, we used QGIS. We loaded it into the program, and we're going to use a tool called Clipper to crop the data of the map. Basically, take away the border. In this slide, we show the clipper command activated. It is focused on the map that we're going to edit. It is the area that we're going to cut out to use. It is selected in red. GDAL or QGIS takes this data and turns it into a command line, which GDAL, in this case GDAL Translate, uses this data to create a cropped version of the terrain that we're trying to use. And see if we can get a closer look here. This is, of course, a closer look, just so you can get an idea of what the the command line stuff is, and the GDAL, and what we're selecting, and how we're in the end is the output file is going to be called the input file. I think it's 03311 6F6, and the output file is the same name with out printed on the side, on the side of it, and that's just so we can discriminate one chunk of data from the other. And we proceed and crop this file. In the end, of course, you're going to get a bunch of these small tiles that you can use for the map. We've also got displayed here the DEM data, which we have here just to show that it's functional and viable. We don't need to trim the DEM data. In the end, we will plaster to have Virtual Planet Builder load this stuff, but we're going to when it comes to building, we're only going to use a certain gaming area, and it's very important at this stage, while you have the graphical representation in front of you, that you get note of the southwest corner and the northeast corner of the map that you're going to generate. This you'll use to calculate the gaming area using one of the commands that OSGDM will use. And it's good to get those points now. Well, you got well, it's very easy to get. There are, of course, latitude and longitude coordinates. Now we can continue and start thinking about our Virtual Planet Builder command line. Before we get too much further on this, we should keep ourselves organized here and put our files in their proper order. We do this by we create basically 3 directories within the project directory that we're going to create. In this case, our project directory is going to be Hemet, so we have a directory in called Hemet, and in there we have 3 subdirectories. In those subdirectories, one of them is going to be dim. This is where you're going to put the 2 dim data files that we collected. We keep the dim data separate from the texture data, so Virtual Planet knows that all the data is that we're going to use to build the actual 3D structure for the terrain is in a particular spot, and we'll just point it. When we go to the command line, you'll notice that we just pointed to the directory. We don't have to point at the 2 files that we're going to build this thing with. Same thing with the texture. All the map textures that we've just called with the QGIS tool will go into a texture directory. And here again, this is to segregate those files in their own little spot. We'll just simply tell the program this is the directory where all the texture files are that are going to be part of that terrain. Finally, we're going to have a terrain directory. This will be sort of like the build area for the terrain itself. Everything that is going to be built in the terrain will be built in that directory, and there will probably be a subdirectory which the program will create itself. And if we have any, say, insert data, which is used in OpenSceneGraph, we will declare those separately. And notably, we will give them, that data, its own little directory. So, but in the basic build that we're going to do here, we're just going to have 3 directories. 2 for data, 1 to build our map in. And that should cover us. So can we get started with our command line? Yes, I think we're ready. We got everything in place. We can start thinking about our command line now. Now we're getting down to the meat potatoes of this thing. We're getting down to the command line. The command line is basically the commands that you're going to tell OSGDEM to what it needs to build the terrain that you're going to try to build. And the way I tend to do it is I bring up a copy of Notepad, because this string's going to get quite long and unwieldy, and doing it under Notepad, or any editor for that matter, is far more ideal. I could just grab this and from a command line just drop it in, hit enter, and OSGDEM should work. I also like to keep a command line, keep a text record of this solely so if something goes wrong, I have something to fall back on. I can look at this and say, oops, this didn't work. In fact, I've sometimes, in my struggle to get the proper command line going, it's not unknown for me to come up with 4 or 5 command line files, and I'll finally go find one that works, and I'll just say, This one works. Oh, and by the way, what you see inside there, that is actually a functional command line for our data. And let's look at do a breakdown on this and see how explain how the components of this will work. So here's a breakdown of the command line, and I'll go through each step here. The first is the geocentric command. This basically tells us our database is going to be geocentric, i.e. whole Earth database. The next command I use is, of course, the map texture, where the map texture data is, and I just point it to the directory, and it knows exactly where all that is, and that is, of course, the -t command. There's another command called the -d command, and that's used to tell the program where all the dim data lives. And in this case, it's user dglen documents map data dim. Want to adjust it accordingly to where you happen to have your dim data. The fourth command here is something I'm going to have to go over with you a little bit. Is called it's the -e or extents command. It basically tells the program where the extents are of the database that it's going to build. And obviously I gave it in a lot of cases I gave it a lot of data, a lot of it's going to spill over, and I only want a certain chunk of it. And this defines what that chunk is going to be. And it starts off with the southwest corner, and then it gives the width and the height in degrees decimal. Everything is in degrees decimal here. And of course I'm going to have to go over and explain to you how to calculate that, and we'll go over that in a moment. The other command is the .a command, and that basically goes over what we're going to call the subdirectory. That we're going to place the paged databases themselves. The structure of a virtual plant builder map is that you got a main file or a master file and a bunch of slave files which resides in the subdirectory, and this is the name that you're going to give the subdirectory. And then for the master file, of course, you're going to use the output command or the -o command, and that will be the output of the master file. The master file is sort of the tie-in to all the subfiles. They're located in the subdirectory, which you just created, named after the .a command. Now, a little subnote here. The subdirectory that you're going to create is going to have a few extra goodies attached to it. This is normal, nothing to be afraid of. So it will not just end with Hemet -test1. It will put a root and an X and a Y sort of thing in there to kind of denote the location. And while we're at it, we might as well talk about the extents command. It is one of many ways that you can determine gaming area using Virtual Plant Builder, but for me it is the simplest. To go over it, You will start with the southwest corner of the database of the gaming area as your longitude and your latitude. Then you will use that data plus the northeast corner to calculate a delta of that will consist of the width and the height of the database. This is, of course, in decimal degrees. Everything in the gaming area is determined by latitude, longitude, decimal. And that's the way the E option works. There's other functions in Virtual Planet Builder, in OSGDEM. You can use the -- help to go over them all and learn how they work, and which is not a bad idea. So we're finally at the point, a moment of truth. We're ready to make some data. We're ready to make our database. We have our command line string all ready to go. We open up our command line shell in the terrain directory for the terrain itself. When you do a copy for the command line string, you want to make sure that there is no carriage returns in the string. This will abruptly start the program prematurely and without all the commands to it, and will lead to probably some disastrous results. Once you paste your command line in the shell window and press enter, the program will start working. It will start by giving you an inventory of what it understands it has for the gaming area. It will then use use GDAL to build some temporary image files, which it uses for building the terrain. After that, it will start the task of actually building the terrain, starting with the master file and working to a finer and finer detail. And so you actually built the bulk of what was referred to as the lowest level of detail for the file first, and then go deeper and deeper until you go to the finest part of the detail. And the program is smart enough to be able to calculate what that level usually is, and that's dependent very highly on what the maximum level of detail of the textures that it's taking on. So you can limit this using a -L command, but you cannot extend this. This is something that OSGDEM calculates on its own. It usually does a pretty good job of it. And so you don't have to worry about this. So the thing continues to crank along, and it will at the end you will know that the program is ended, because it will report the time that it used to build the terrain. And now at that point you can go in and with OSG Viewer go in and check the results. And when you start off, well, it won't look like this, but it will look pretty close. Oh yes, we will take a look. And we already have. So One of the first things you want to do when you open the database up and get relatively close to the database with the center mouse button is you want to press the four key. The 4 key puts OSG viewer in the terrain mode, which is the way you want to test this database. This will also make the terrain a lot easier to see close up because, you know, otherwise you get a tendency to go punch right through the database and go on the other side, and that's not fun. You want to glide over this thing just like, you know, you're flying over with like a small airplane or whatever, and get up close and dirty with the database, with the terrain. One of the things you might want to try out is the W key. The W key will put the database in wireframe mode. With this, you can go in and view the structure results, which could be quite interesting. It'll also be the indicator, a more obvious indicator that the DEM data has indeed taken effect, and this is how it's built the structure for the terrain. So, a few things. Now we build our terrain, I'm going to bring up some stuff for further study. One of them, of course, is the open source Geospatial Foundation. These are the people who have created QGIS and GDAL. Here's more stuff that is useful to check out. One of them is, of course, from AlphaPixel. You could probably, if you can't see this, you could probably Google it just by my description here. You know, AlphaPixel has an excellent paper on GDAL and OSG DEM, and there's the link to it. There's another author, another tutorial on OSG DEM on the OpenSceneGraph track website, as well as a few instructional pages from a couple of very nice people. I will try to, of course, this here is pointing out my fulfillment of putting in YouTube videos. That's why you're watching this. And I'm going to try to find a place for the slides. I'm tempted to put them on Facebook because that's probably an easy place to find them. Also, a few more places to check out. This is the FCC latitude and longitude calculator. It's very useful for taking degrees, minutes, and seconds and turning it into latitude and longitude in decimal form. There's, of course, the GDAL web page, which is always useful, as well as the QGIS web page. Virtual Planet Builder's original author can be reached through the OSG forum, and there's a link to that. I'd like to give thanks to Robert Oldsfield, who started this project, and the many others that volunteer their time to maintain and improve Virtual Planet Builder and OpenSceneGraph, I should add. Special thanks to Robbie Allen for letting me use his character, the little character that you've been seeing appearing over there. That is Shelly. That is one of his. I did a 3D representation of it, but he originalized the design and guided me on making her. And with that, I thank you for watching this video. Have a good day.